control search, and he also talked about pattern recognition in terms of neural networks, which is what today is called deep learning. So Marvin sort of laid out what are the problems to build artificial intelligence. So inspired by that, I thought, if I'm not going to be a grumpy old guy, maybe I can talk about steps towards superintelligence. And so that's what this talk is about. How do we get to superintelligence? I'm saying it's going to take a long, long time, but even if it's going to be a short time, we still have to get there. So how do we get there? What should people be working on? So that's what I'm going to talk about. This is the outline of the talk. I'm going to start with this brief history of artificial intelligence. And Alan Turing is really, I think, a founding figure in artificial intelligence. There are two well-known papers he wrote. One in 1936 on computable numbers, which is really where he came up with the structure of what computation is and what a computer is. And then there's a fairly well-known paper in 1950, Computing Machinery Intelligence, where he introduced what we now know as the Turing test, which I'll talk about. But Marcus, he wrote a paper in 1948 that his lab director wouldn't allow to be published. His lab director, by the way, was Sir Charles Darwin, who was the grandson of that other Charles Darwin. But he thought it was too radical an idea and wouldn't let him publish the paper. And it didn't come out until 1970, well after his death. And in that paper, he said, in 1948, the possible ways in which machinery might be made to show intelligent behavior are discussed. The analogy with the human brain is used as a guiding principle. So he was really talking about how do you make something as smart as a human being in 1948. And he said we're mainly concerned with discrete controlling machinery, and what he meant by that is essentially a Turing machine, essentially a computer, a digital computer. He hypothesized that that was how we would build artificial intelligence. I think that's a question, but I'm not going to talk about that today. And he said brains very nearly fall into this class, and I think he's a bit wrong there too. But nevertheless, that's what he thought. In 1950, he wrote a paper that was published, Computing Machinery Intelligence, and he admits that, well, maybe he doesn't have very convincing arguments, but it was speculative. And, you know, he thought extrasensory perception, i.e. mind reading, was a proven thing in 1950. And he talks about it multiple times in that paper. Actually, go back for a second here. No, I didn't have it highlighted. Right at the start there, he talks about the imitation game, which is the Turing test, and I'm going to talk about that in a minute. So he said, we can debate the question of whether machines can think, and here's the summary in the second underlined red piece there of what he sort of came up with the imitation game. Basically was, if you're talking over a teletype, or, you know, call it instant messaging, if you're talking over instant messaging and you can't tell whether it's a computer talking to you or a person talking to you, then the thing at the other end, you may as well say it's thinking. If you can't tell the difference, you know, that's thinking. Maybe it's not thinking exactly the same way people do. So that was his test. And he said that he thinks that with a storage capacity of about 10 to the 9th, 1 billion bits, we'll be able to get computers to do this. And he goes on into a bit more detail. He says he'd be surprised if 10 to the 9th, more than 10 to the 9th, more than 1 billion bits. What's 1 billion bits? That's 100 megabytes or so. You won't need more than 100 megabytes of code, it turns out. And the way he comes up with that is he says that the 11th edition of the Encyclopedia Britannica has 2 by 10 to the 9th bits of information in it. Somehow that gets converted to code. So he was a brilliant man, but I don't, you know, in hindsight, I don't agree with everything. And he said at the time, and this is 1950, computers were really, really slow then, you know, about 10,000 instructions a second, maybe 50,000. He said, it's probably not necessary to increase the speed of operations of our current machines. And he also said, underlined in yellow there, that he could produce about 1,000 digits, he means bits, 1,000 bits of code a day. Now, 1,000 bits is not that many bits, it's about 128 characters. Why could he only produce that much code per day? Because there weren't assemblers even. You had to program in binary. So, you know, 1,000 digits of program a day, and then he divides that into the 10 to the 9th, and he comes up with 60 workers working steadily through 50 years might accomplish the job. And if you do the division, it means they got every second Sunday off, because it's about 333 days of work per year. I think that's English working conditions. That's why we left. But he thinks that 3,000 person years is right at the bottom there. Some more expeditious method seems desirable. He thinks that's too long. 3,000 person years. It's got to be quicker than that. By the way, that 2 by 10 to the 9th bits in the Encyclopedia Britannica, I actually have the 11th edition of the Encyclopedia Britannica in my living room, and I counted, and it is, I came up with 1.7 by 10 to the 9th bits, so it's pretty close. I don't think anyone's ever checked him on that before. So that was 1950. 1956, John McCarthy, in a proposal in 1955, said we're going to have the Summer Artificial Intelligence Project. And the very first sentence up there says, we propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956. That's the very first time the phrase artificial intelligence has ever been used that I can find that anyone seems to be able to find. And he didn't feel the need to explain it. It was sort of a naturally explainable, self-explaining set of words. He said the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. And he means digital computer, he goes on to explain. And he says, we may need some more memory, we may need slightly faster machines, but it's really about knowing how to write the programs. So they were very optimistic that it was, not too far around the corner. So over the next few years, there have been what I categorize as 4 approaches to artificial intelligence. And I apologize to everyone here who works in artificial intelligence. I'm going to give cartoon versions of these. Anyone who works in the field will be able to say, well, that's, you're not accurate. I'm not accurate. It's a cartoon version. So let me explain these 4 approaches. The first is the symbolic approach. The symbolic approach is using symbols. What is a symbol? Well, you can think of it, if you're a C programmer, as a struct, a thing with some things attached to it, and you can test whether one struct is equal to another. Maybe it's got a name field. And so you have stuff like this, where the bolds are the symbols. So every instance of a cat is an instance of a mammal. Fluffy is an instance of a cat. So now we can conclude with a pretty straightforward rule of inference that Fluffy is an instance of a mammal. So symbolic. The power of symbols is that there are these abstract things which can tie together different domains. If you know something about a cat, you know that it's got 4 legs, you know that it's a mammal, that you know that you can tie those together. It's a mammal with 4 legs. Not all mammals, if you count marsupials, have exactly 4 legs. But anyway, but inside the machine, there is no catness. There is no mammalness. It's a symbol. The name of the symbol is something that we as humans read, and when we read it, we give a lot more meaning to it. Inside, it's really something like this. Every instance of a G0537 is an instance of a G0083, etc. And that's what the machine is manipulating, and we read the symbols and apply more understanding to it. Now, it's still important that you can have knowledge from 2 different domains, and you can couple it together with G0537 or CAT and get the knowledge to flow across. But in fact, it's slightly more pernicious than that, because we've got instance of these things in italics there, and really inside the machine, they're just named rules which have a certain algebra associated with them. So really inside the machine is for every x where R0002 of x and G0537 then, and so I've just translated that. So that's what's going on inside, and we give meaning to the symbols. We're the ones who ground the symbols in meaning. Neural networks. Neural networks come at this to try to give another way of grounding meaning. And maybe I shouldn't call it the second approach to artificial intelligence. There have been so many versions of neural networks, 2.0, 2.1. Marvin Minsky in 1954 wrote a PhD thesis on neural networks at Princeton. We had very many generations into the 80s with back propagation in neural networks. Jan LeCun was here, and we've had 9 years ago, deep learning came out as the latest version of neural networks, and it has had a big impact on the world and will continue to have a big impact on the world. But I'll nevertheless criticize it a little bit in a minute. Now, the idea with neural networks, well, first the word neural comes from a 1943 paper by Pitts and McCulloch and Pitts. It's not really much like human neurons at all, although the press sometimes says it's based on the brain. Not really. But the idea is you've got these little model neurons, take some input from something, and then the neurons on the right-hand end that light up the most are the category. So each of those neurons, model neurons, is a thing with some weights. It takes some inputs, it multiplies the inputs by the weights, makes the linear weighting of those inputs, gets a sum, shoves it through a little function which compresses it down to be in the 0, 1 range, and then the output neurons are labeled with things like cat, or G0537, but we put cat there, dog, car, etc. And when the input is maybe a picture and gets fed in some way on the left, whichever neuron on the right has the highest score says, okay, it's a car in this picture, or it's a dog. Recently, deep learning has come along, and people hear deep and they think, oh, it's deep like people, it's deep. No, deep means more layers. We could only handle 2 or 3 layers in the 80s. And a few people worked on it for many years, and then a few years ago came out with 12-layer networks, and now we have many more layers. But one of the things that's changed is that in the old days, the input, such as an image, that Volkswagen there, was first processed by some pre-processing programs, which were written by people, which might find circles and straight lines and stuff, and they were the stuff that went into the shallow network, because there weren't many layers, and they were the inputs. Oh, there's circles, there's lines, there's whatever there is. And that would go to the car or not car output. In deep learning, you just effectively take the raw image and let the network also learn what it needs to extract early on. And this has been revolutionary for some things like speech understanding. The reason we have the Amazon Echo Alexa in our homes and it can understand our speech is because the deep learning network replaced the hand-coded early processing of the speech signal with something that was learned on what are the right features. I think people have gone overboard now to think that, okay, we never want to tell the networks anything up front. We want them to extract everything because of that success in speech understanding, for instance. And I'll come back to that later. Deep learning, as I said, it's been around for about 9 years, but it really got introduced to the public in a 2014 article by John Markoff in the New York Times. This is an example from a Google system where the Google program sees this image and labels it a group of young people playing a game of Frisbee, which is pretty damn impressive. And I think that surprised a lot of AI researchers when they saw this result. We were not expecting this to come along that quickly. And that has been a big positive thing. I'm going to lump in, this will make some people annoyed, I'm going to lump in to neural networks other sorts of machine learning like reinforcement learning, which was first done in 1961 by Donald Mickey. He was at Edinburgh University. They couldn't afford a computer, so he built one out of matchboxes. But traditional robotics, the third approach. In traditional robotics, it was really inspired by Larry Roberts at MIT in 1963, where this is the one image he had in his PhD thesis. You can see he reflected it by mistake in part B, but it was too expensive to make another picture. At that time, to get an image into a computer, you took a picture with a film camera, you got the film, you put it on a cylinder, and then had a single bit scan across as the cylinder turned back and forth to get the gray levels. And he was able to get from an original picture to a model of a polyhedral object. And that got people excited. Okay, we'll just figure out how to take line drawings, the edges, and we'll build vision systems which can understand what that means. And there was a whole flurry of work in the 60s and into the 70s with images like this, not real images. But then they said, okay, now we can convert that, run it on a robot. This is the only image I could get of the copy demo from MIT, where a camera was trained at a pile of blocks, and the robot then built a copy of that pile of blocks. By 1970 at SRI out in Menlo Park, they built this robot, Shaky, and Shaky lived in a world of polyhedral objects with matte surfaces, so they were easy to see, and it made plans of how to avoid them, how to stack them, how to push them, etc. By 1979, Hans Moravec had the first real robot that could move and avoid obstacles. I took this photo in 1979. There's Hans taking a picture of his robot running. Normally, he ran the robot in the dead of night from midnight to 6 a.m. I was his helper for that. And in 6 hours, the robot would move about 20 yards, 1 yard every 15 minutes, processing it on the mainframe. Why did he do it in the middle of the night? Because everyone else had gone home, so he got the whole computer to himself. We're about to shut down the AI lab and move it down to campus on Stanford. So the special dispensation for the only day ever that a single student got to use the computer all day was this one day in October of 1979. And he had the first outdoor run of his robot. But he still thought polyhedral objects are a good idea. And then what really went wrong was a really strong feature in these images that it would get is the shadows. And they moved in 15 minutes. So it was a troublesome day. This is another robot of the era. This is at Edinburgh University. This is Freddy. And you can see it's playing with blocks, which are cylinders and flat things. By the way, that hand is 1 meter wide and 1 meter high. That is not a miniature camera. That was a full-scale camera at the time. You know, it's about 50 centimeters long. So that's traditional robotics. And so traditional robotics didn't have symbols or names for things, but it related what it was doing to actual physical stuff that it could sense. And then there's what I call behavior-based robots, and I put the foundation of that is 1950, an American in Bristol, Gray Walter, who was actually a neurophysiologist, but he tried to build imitations of life, as he called it. This is from his 1950 4-page article in Scientific American with his little tortoises. So he built these mechanical tortoises. You can see on the up here the circuit diagram, and you may not recognize this. This is what is called a vacuum tube. This is a little filament that lights up like inside an incandescent light bulb, emits electrons. The anode here collects them, and there's this grid in the middle, and you can control the flow, and you can make an amplifier out of that. That one's got one grid, this has got two grids. And just with these two elements, this particular robot had all sorts of behaviors because he used the nonlinearities of those two simple elements. And he showed all these behaviors and how they came about in his 1950 article in Scientific American. A year later, he came back with another article and added learning to the machine. He added extra vacuum tubes, or valves as they're called in the UK. And here he had a whole set of experiments like Pavlov, where you condition the robot to think it's going to get kicked whenever it hears a whistle. Pavlov did it with dogs, and he fed them whenever he blew the whistle. So the idea there is it's not a thing that tries to have a representation of the outside world, but just reacts to the outside world. And in 1985, I took a digital version of this, and I started layering behaviors which connected sensors on the left to actuators on the right, but didn't worry too much about what the other behaviors were doing. So, for instance, if I'm trying to get somewhere, I'm not consciously thinking about moving my feet. I've got a different layer that just does the foot moving. Now, I'm trying to get somewhere, I'm late. So I give instructions to my lower levels, go faster, but I'm still not deciding where to place my feet. There's sort of separate processes running. And that was the idea with this behavior-based approach, where you've got multiple behaviors running. You don't necessarily resolve everything. As I'm running, because I'm not thinking consciously about where my feet go, they just go where they go. And I manage to deal with that if I put my foot in a puddle or something. And I built networks out of little elements of finite state machines. This is for a 6-legged robot called Genghis. There are actually 57 finite state machines built in this layered network, and that robot could walk over rough terrain. That led directly through a series of processes. The first business model of iRobot was a space exploration company. That was what we were doing. We also had started a project out at JPL, which eventually turned into Sojourner. And Sojourner was launched in '96, landed on the moon in '97. For the first 28 days was under ground control, and then it was put under behavior control for the rest of the mission. Here it is on Sol 72, out there exploring Mars by itself with this behavior-based approach. And then that turned into the Roomba, ultimately, which you can still buy. The IED robots in Afghanistan and Iraq, there were 6,500 of them we had there. This is in Fukushima, March 11th, 2011. There was the earthquake and the tsunami, and the Fukushima Daiichi plant was in terrible shape. A week after it happened, we were asked if we could help out. We got some robots there in 48 hours, and the robots helped shut down the plants, and they were these behavior-based robots. And one of the big ones there is the world's biggest Roomba. It's a 200-kilogram rover, and it was sucking up radioactive dirt. They're still there. I've visited Fukushima. And then the robot Soya from my recent company. But something happened along the way. These behaviors that I'd had, which mixed up control and state machines, got simplified by two people, Damien Isler and Bruce Blumberg, and they turned it into something called behavior trees. And behavior trees were a much better formalization than I had. We used it in my company as the internal language for the robots when we taught them by demonstration. They automatically, when we showed it something, it would automatically build a behavior tree, which you could then go and modify. But the real stuff is that it's been adopted by the gaming industry. So two of the best-known platforms, and I know you're using Unity here for some things. Unity and Unreal are the two big platforms for video games. They both use behavior trees, and over 2/3 of all video games are now programmed in one of those two approaches. So the reason I wanted to talk about this, people have heard of behavior-based approach, but it actually has turned out to be very successful. If you count the number of entities, all the little bad guys in every game is a part of a behavior tree. They're programmed in that. So these four approaches, I sort of summarize here what they can do. Symbolic is very deliberative. You reason about things. You apply rules. The neural networks say, I see a cat. Robotics, traditional robotics is rather deliberative. And with behavior trees, the behavior systems can both react to the world and be deliberative. But how do they, what are their strengths? And here I've just sort of put on a scale of 1 to 3. The symbolic systems are great at composition because those symbols let you compose different modules together. There's a way to link them together, whereas the neural systems, the behavior systems are lousy at them. Grounding, the symbolic systems are not very good, but the neural systems are great. So I've got a bunch of scores here. But then I thought, I did a very scientific study to compare this 1 to 3 scale of these four approaches to a human child and came up with this. I think we're a long way from true intelligence with these systems. And people are really bad at predicting the future of AI. And I wrote a blog post, and then I had an article, a version of it in Technology Review, on the 7 deadly sins of predicting the future of AI. I'm just going to give 2 of them today. Why people get it wrong, why people think we're so close to true intelligence, and maybe are not. I'll start with performance versus competence. If we see a person looking at images and writing labels like that, we have a way of sort of generalizing what competence they must have. We'd think, for instance, okay, if they saw that picture and they could write down the description, a group of young people playing a game of Frisbee, surely they would know things like, what's the shape of a Frisbee? That's a circle. The program that did that labeling didn't know the shape of a Frisbee at all. How far can a person throw a Frisbee? You know, any human who talks about Frisbee sort of knows roughly. They know it's not 87 miles. They know it's probably more than 3 inches. They've got some idea. Can a person eat a Frisbee? We know that. This program doesn't know that. It doesn't really know what weather is. It can say it's a snowy scene, but it doesn't know snow is part of weather. It would be weird if a person couldn't answer those questions if they could do that labeling. And the problem is there's performance of a task and general competence. You know, when Deep Blue, the chess playing program, beat the world chess champion Kasparov in 1995, people said, game over. Artificial intelligence is going to destroy us all. It had great performance, but it didn't have the general competence that a person who's a world chess champion had. And part of it is because, you know, it's based on probabilities that get linked together. This is what those neurons are linking. And yeah, you know, 90% chance that's a person on the horse, 60% down below. But none of us think there's a 20% chance that this is a person. And so this has now become a game in the publications where you have adversarial tests. Here's a labeling system. It said that picture on the left is a guitar with 99% probability. The picture on the right is a penguin with 100% probability. And then using artificial evolution, tried to evolve images which got good scores and there's a guitar with 100%. Oh, that doesn't look like a guitar. There's a pair of a real baseball and a fake baseball that this network triggers on. And you can sort of see, I like this one. You can see the school busness of it, but it's not really a school bus. It doesn't have the spatial understanding, spatial coherence. And these image labelers, they're not seeing the world. They're labeling the images with appropriate English words. And you can sort of see as you look at these, oh yeah, I see why it got that wrong, but no human would make those mistakes. And it's not just adversarial training. This is from a paper that came out on November 28th. These are real images labeled. Now, yeah, you can see why it thinks that might be a snowplow. It's a yellow thing across a road and there's snow around. But it's not a snowplow. We know that. So it's very different. Second mistake, people, it's got performance of labeling, but its competence is lousy. Here's another example of what we get wrong. Suitcase words. Marvin Minsky came up with this, suitcase words. We use English words to mean many, many things. And so these are some of the things that have been said about AI systems in the last few years. Institutional publicity officers, when one of their professors comes out with a paper that can sort of hallucinate something, they want to put out a press release. Our professor came up with, figured out how hallucination works and put out a much stronger statement. But each of these words means many, many things, and you get a little aspect of it, and then people overgeneralize. So learn. Learn is a big word, but learn means many sorts of different things for a human. Learning to play tennis is actually different from learning to ride a bike, although they're both physical. They're both called learning. Learning ancient Latin, that's very different from learning to ride a bicycle. Same as with algebra, you use a blackboard, but it's a very different skill. I'm really good at algebra. I'm horrible at Latin. So I could learn one and not the other. Learning to play chess is yet again different. Learning to play music, yet again different. Learning your way around a new city. We use these suitcase words, and when we get a little bit of success in one aspect, people tend to think everything's solved about learning, but it's only a tiny little piece. I had my VCs, my venture capitalists, would routinely call me up with what I called venture capitalist calls. Such and such, their robot learns. Does your robot learn? No. But anyway, I'm not bitter, really. So now let's go beyond the Turing test. The Turing test was this idea in Turing's imitation game, and it actually starts by comparing a man and a woman, can sometimes fool the interrogator about who's a man and who's a woman if you're instant messaging. If a machine replaces one of these people, sometimes it can fool them. Then he generalizes, says, well, if a machine you can't tell the difference between a machine and a person, then you have to say the machine is thinking. Since the person is thinking, you can't tell the difference. So that's it. Now, some people think that he wrote about that as a rhetorical device to break down the idea that machines couldn't think and say, well, at least in principle, it's possible we can make machines think. But he talked about how to construct a program for such a machine. We've already talked about the 3,000 person years of programming. Suggests that it's maybe better to have the machine learn like a child and then playing this imitation game. So he treats it as a real test. And we've seen the Turing test be applied as competitions. But what happens when competitions do it? People figure out how to hack the system, and they do chatbots that can fool people, because people actually are easy to fool on lots of things. And so it hasn't really been an effective test for intelligence. So I think it's time to replace the Turing test. If we're going to make progress towards superintelligence, I want to talk about tasks that any human can do, or most humans can do, and let's see if we can get the machines to do them. Now, it may take many decades to get there. But the two examples that I want to give are an elder care worker, which is an embodied robot, and a services logistics planner, which is a disembodied program. And you might say, well, does your superintelligence have to be able to do both of these? Well, if it's better than a human, it better be able to do everything a human can. So let's see if it can do it. So an elder care worker, live-in care provider for an elderly person over decades. And why over decades? Because, you know, when it starts working with a person, maybe the person can say sentences that Alexa can understand, but, you know, 30 years from now, when I'm still trying to update my blog about whether I was right or not, you know, I'm going to lose a lot of capability of getting nouns, and I'm going to be pointing, the thing. And so, you know, Alexa-type language understanding is not going to be good enough at all. So it's got to adapt to a lot of stuff. It's got to understand human relationships and expectations in the household. You know, does it let my daughter in? Yeah. Does it let some random person off the street in who just wants to come in and steal stuff? No, it shouldn't do that. Got to provide physical help to the person, which is whole body manipulation. You know, as I get older, get me into and out of bed, etc. And we've talked about the degrading language. Understand how to provide for human needs. Identify and manipulate every object in the house. Recognize when it needs help and how to get it. So, you know, the light bulb's out. Oh, I better get the electrician in. So it has to understand the world at a much deeper level than any of our systems can at the moment. A services logistics planner is a program that you can say things like, we need a new dialysis ward in this hospital. Can you design the dialysis ward? That's the specification. Let it go and figure everything out. It's got to be able to do geometric reasoning and design, including meeting all the standards that you have to have in a hospital. It's got to do quantitative physical simulations of how the space will work, understand human needs, understand how family members coming with dialysis patients, etc. And you don't want to have to tell it all this. It's just like if you have a, I'll get back to that. But this is a sort of task a colonel in the US military is often given in a terrible situation. Oh, we need a new hospital ward to do such and such, and the colonel is expected to figure it out without more specification. So a human can do this. The elder care worker, and there's going to be a lot of pull for this because so many of us are getting really old, and there's a demographic inversion. You know, it needs to be able to help people. This is what you get when you Google elder care worker. The real life is not as happy as this for those who've been in elder care facilities. But you need to be able to give physical help to people. You need to be able to manipulate their bodies, not hurt them. You need to be able to respond to their commands while you're doing it. Stop! That hurts. Sometimes it's being grumpy. Sometimes it's not. Knowing when to push through, when not to push through. If someone needs help getting into and out of bed, they probably need help getting into and off the toilet, onto and off the toilet. It's not as happy a situation as this, but this elder care worker's got to do all these things and provide physical services to people. The services logistics planner, as I said, an Army colonel is my model. Got to figure out, what's a dialysis ward going to look like? What are the requirements? You have people in beds. You have, are you letting the family members in? How many of these machines do you need? How tightly can you pack them? Are you using beds for the patients? Are you using chairs for the patients? Have you got, is it like a 2001 space station with lots of room, or is it more realistic? Who are the technicians that need to help with dialysis? How many of them do you need? What length of shift do you need? All sorts of questions about how you lay things out, how people flow around, and all the sorts of things you have to worry about. Very complex thing. Now, if we are going to have an artificial superintelligence, it ought to be able to do this. It's a very hard task. There's a lot of things you need to do that we can't do with our AI today to get there. So what's hard today? Here's a set of things that I've said are hard. I'm going to talk about the first 3 of them. And I'm going to do an experiment on you in a minute. So real perception. We've got image labeling, but is that really perception? We've seen these weird examples where, like, the third one on the top from the right comes out as an armadillo. I don't think anyone else here made that mistake. But here's from a Senate hearing earlier this year. This is a Senate hearing about a vision system for an autonomous car that's out on our roads. And that's a senator over there. And here's a stop sign which has been hacked with some pieces of tape. And you can sort of see that's sort of 4-ish, and that's sort of 5-ish. And when the vision system on the autonomous car sees this, it thinks that's a 45-mile-per-hour speed limit sign, which is a little different from stopping. So this can have real consequences. Now you look at that, you say, how can it make that mistake? It's a red sign. Speed limit signs are white. How could anyone make that mistake? Well, it turns out red is not necessarily red. We think in the category red. And we think about the category red for a good reason, but it doesn't mean the pixels we sense are red. So here's an example. And so, I'll get to the example next slide, sorry. So what's going on with deep learning is it's replaced the knowledge that we have as human psychologists and designers of algorithms with just something that's learned. And you can only learn when you've got examples. So here's the example. What is this? Anyone want to tell me what that is? I'll repeat it for the audience. What is it? Cylinder on a chessboard. And why? So Marcus says it's a cylinder on a chessboard. Why do you think it's a chessboard? The checkers, with the black and white squares. Well, yeah, except, there's a black square, there's a white square, right? And you know what's going to come now. They're exactly the same. They don't look the same. Our brain is processing backwards, sees the shadow, and compensates. But if we start covering some pieces up, they were the 2 pixels, exactly the same color, but in context, they look black and white. There's the bits from that on the right. Our brain does something smart because it's not direct from pixel values, from darkness or color that makes something what we perceive. With good reason. It's because lighting conditions change all the time, like the shadow, and our brains are good enough to compensate for it. What is this? Strawberries, what color are they? They're red, aren't they? Guess what? There's 750,000 pixels there. There's only 122 where the red component is more than both the green component and the blue component. Here are the 3 pixels where the red component is strongest and more than both the green and blue pixels. Here are the three pixels with the biggest red component. Now you might think, well, this one's got a bit of a red tinge. Yeah, but watch this. For those of you who think that, when I get rid of the distractor there, the redness goes away. Okay? Your brain was putting the redness there. So it's not really red strawberries, but we figure out it's red. And why did the machine learning system not know that traffic signs were red? Well, in different lighting conditions, the pixels are not actually red, but we use this thing, we humans use this thing, color constancy, to compensate for the different lighting and figure out when something's red. So for us, yeah, stop signs are always red. For this algorithm, there are all sorts of different colors because it's just looking at the raw color. So there's a case where too much letting the learning happen without giving some training wheels on color constancy leads you astray. By the way, we want this robot to work in a person's home, and people often have, when they're writing their AI algorithms, this is the sort of simulated home they might have. But as my student Aaron Edsinger pointed out, real homes are a little different. And there's a lot of stuff. But even so, when we see that, we know that's probably salt, right? And that back there, that little tiny thing, we know that's probably a rice cooker because we go from knowing stuff to projecting stuff. None of these learning algorithms can do that. Who knows here? Who knows what steampunk is? More importantly, who doesn't know what steampunk is? Okay, you're my people. I'm going to train you in steampunk. Okay? I'm going to train you with 3 examples. This is steampunk. This is steampunk. Look at these examples carefully. This is steampunk. And by the way, you find steampunk at maker fairs a lot. So there's 3 examples of steampunk. Now we have a test. This is people from the maker fair. Is that steampunk? No. All those steampunk examples had funny goggles. Is this steampunk? No. Is that steampunk? Yeah. And, well, he does have those goggles. He's got those goggles down there. Steampunk. They've got funny goggles. Steampunk? Steampunk? Yeah, maybe a bad try at it. Funny goggles? No. No goggles at all, but it is steampunk, right? It's something totally different, but we know. And so I gave you these 3 examples. You were able to get a category. The machine learning perception typically has 1 million or 10 million examples, each shown 100,000 times. Humans learn this new category, which is not a well-defined category at all, in 3 examples. Real manipulation. We can't do that. This is from the Stanford Hand-Eye Group in 1978. And you see on the right there what we called the blue arm. Off picture is the gold arm. I happen to know it's there because that's me in 1978. And the gold arm is currently in the front lobby of the Margaret Jacks Hall at Stanford University. There it is, the gold arm, with an electric gripper on it. And that's what we used for our experiments in robot manipulation in 1978. And, if you look at that gripper, it's parallel jaws on ball screws going back and forth that used to jam up and you had to oil them all the time. This is what my company was selling for grippers this year, parallel jaws on ball screws with advice on where to apply the lubricant. 40 years later, same thing as we had before. We sold kits to outsource the problem of getting the right gripper. Nothing like a robot hand that can do this. It has to be a special purpose gripper. We had kits. Other companies like Shunk have about 1,200 pages of catalog of different grippers that you can buy for manufacturing. We haven't made any progress on manipulation in 40 years. We're really, really bad at it. And manipulation is important for any physical superintelligence, especially the ones that are going to kill us all that they keep talking about. They need hands. A lot of human knowledge can be found in books and video tutorials. And so you see people say, if we can just get our programs to read, they'll be able to get knowledge about the world. And sometimes, as the press does, someone had a program that could read certain things and answer certain questions about text. Millions of jobs at risk? Probably not. But why is it so hard? These are called the Winograd schemers from New York University. We can read that sentence. Alice tried frantically to stop her daughter from chatting at the party, leaving us to wonder why she was behaving so strangely. Who's she? Who? I think it's actually Alice. Well, that one didn't work very well. But if the daughter was barking, then it's definitely Alice, definitely the daughter who's behaving. The delivery truck zoomed by the school bus because it was going so fast. Which was going fast? The truck, yeah. But if it was going so slow, it becomes the school bus. Sam pulled up a chair to the piano, but it was broken, so he had to stand instead. It is the... But if he had to sing instead, it was the piano. So here's there's hundreds of these, but the example is that you have to know a lot of common sense stuff about the world to understand books and to understand sentences, because writers assume you know a lot of stuff. Prince William is taller than his son, Prince George. We just know that. We know that we won't know whether that's true or not in 20 years yet, which is a complex meta sort of thing. But, we know that dolphins eat raw fish, so do some humans. We know that dolphins don't usually eat cooked food. We just know this stuff. You don't have to be trained in this stuff. We just know all these things. And, our AI systems have very little common sense. John McCarthy started working on it in 1958. We've known this problem for a long time. We haven't made much progress. DARPA just announced a $2 billion research program on artificial intelligence. And the first $200 million, the RFP out, is for a common sense program. And this is, they ultimately want to have all these domains, but the first $200 million is for objects, agents, and places, understanding common sense knowledge about objects, agents, and places. And this is their chart of all the things that they want the performers to do. And you look over here at these months. What are these months? It's not for the project. That's for what children can do at those ages. And so that for $200 million, they want to make progress towards what an 18-month-old understands. And it's going to be a really hard problem. I don't think they're going to succeed with this. They'll make some progress, but it's really hard. We just do not have common sense. So we can't read. We can't have our programs just read stuff and learn by themselves. Everything we get our programs to do, we have to handcraft. Okay, so that's the negative. So what should we work on now? What should we work on to get towards superintelligence? And I sort of like that idea from DARPA, working on what children can do. So I think if we can make progress on any of the following 4 areas, we will be a lot further along towards general intelligence and superintelligence. The object recognition capabilities of a 2-year-old child, the language understanding capabilities of a 4-year-old, the manual dexterity of a 6-year-old, or the social understanding of an 8-year-old. Now, I'm not saying, start a program, a research program on necessarily on social understanding. It's going to come from many different submodules, but if we can see how we're making progress against these benchmarks, we'll know whether we're making progress. In the same way, DARPA wants to measure against the common sense of an 18-month-old. So let's talk about these. These are short-term things that I think we can make progress on over the next, short-term 40, 50 years. So 2-year-old object recognition. A 2-year-old has color constancy. They know that a stop sign is red when they see it in a shadow, when they see it in a headlight. They can say, that's red. They know that color under many, many different conditions of what the pixels look like. They can map from form to function and act on that function. So, they look here and they can see, yeah, it's not a chair, but I can sit on it, form, function. They can do that sort of mapping for lots and lots of things. They have object classes and can categorize objects that look totally new at the pixel level. So let me give you an example. Suppose you've got a 2-year-old who's never seen a giraffe. They're at the zoo. They see a giraffe for 10 seconds, a real giraffe, say. After you've taken them home, they'll be able to recognize giraffes in pictures from that experience. They'll, like you guys did steampunk, they'll be able to recognize from cartoons a giraffe. They'll be able to recognize very different visual representations of that object class. And you won't need to, when you're at the zoo, in front of the giraffe, you won't need to say, oh, by the way, this is an animal. They'll know it's an animal. They'll immediately know it's an animal. They may not know it's a mammal. So they can do this one-shot subclass learning from many, many different sources. 4-year-old language. 4-year-old can talk and listen. Sometimes it doesn't seem that way. They know when they're calm about turn taking, because we take turns when we're communicating. They understand the cues of whose turn it is to speak. They don't necessarily obey them, but they know them. They know when they're in a conversation with someone and when the participants change. So if they're talking to 2 people, one goes away and another one comes in, they know it's a different person. Alexa doesn't necessarily know that, doesn't know that whether it's talking to 1 person or 2 people. It's just voice to text coming in to Alexa. Kids know a whole lot more. They know how to, if there's multiple people around, they know how to direct to an individual and know when someone is directing at them. They know who's trying to communicate with who. They can tune in on other conversations. They can hear ice cream out in the kitchen. They know when someone's speaking differently from normal, and the elder care robot better know that. If Rodney's, slurring his words really badly one day, oh, this is something wrong. And a 2-year-old can know when you're talking differently than you normally speak. And they understand complex sentences, a 4-year-old, sorry. They understand complex sentences and apply common sense understanding to both tense and hypotheticals. They understand that. So it's much more than Alexa can do at the moment. Much, much more. In fact, not Google, I sound like someone in the House of Representatives. Amazon has a competition out for sustained conversation because they just know they can't do it at the moment. A 6-year-old, manual dexterity. 6-year-old can reliably estimate from vision how to pick up many objects. A 6-year-old sees this, they know they can, a 6-year-old can pick this up with 1 hand. A 6-year-old who has to pick up this thing, when they see it, they don't try to pick it up with 1 hand, they go with 2 hands. And, if they have to pick up a giant teddy bear, they know it's full body. They're going to use their body, pull it against their body. They know that. They can see how to do that just from visual cues. They pre-shape their hands for grasp. They don't come like this. They come like this with the right orientation of the fingers. They don't come like this to grasp. They come like this. They can apply and control force appropriate for the task. Well, a child probably couldn't do this, but you can imagine something that they could grab too hard and just break. And they don't do that. They can guess what they need to apply and adjust it as they lift, adjust the force and grip strength. They can use tools. 6-year-olds can use chopsticks if if their parents have given them chopsticks for a long time. They can use a wrench. None of our robots can do either of those things. They can operate and close many containers. They can open and close many containers. They can operate faucets. They can cut vegetables, wipe down tabletops, open and close closets. They may not want to, but they can do it. They can pick up cats and small dogs without hurting them. This gets back to the elder care worker picking up people, putting them in bed, helping them. But 6-year-old is pet safe. A 6-year-old doesn't hurt a pet accidentally. And this is important. They can wipe their own bums fairly reliably. It's great for parents, but that's an example of what our elder care worker's robot is going to have to do with me when I'm in my 90s. So 8-year-olds can articulate their own beliefs, desires, and intentions, and they understand, an 8-year-old, not necessarily a 6-year-old or a 4-year-old, an 8-year-old can understand that a different person can have different beliefs, desires, and intentions from them. They don't project themselves onto everyone. They understand that individuals are different, and they understand what another individual knows from having observed what that person observed. So they can deduce these things by observing the other person's actions, and they can deduce what other people believe that is different from what they believe based on observing what the other person was able to observe. So if they've seen something change in the world that the other person didn't see, They don't think that a person knows what changed in the world that they saw change, the false belief task. And again, we don't have anything in our AI systems that begin to come close to this. So I think these are good things to work towards, good measures of what our AI systems can do. And some people who used to work at Bell Labs and have done very well with deep learning networks tend to say deep learning can do it all. I'm not so sure. Now, where will things go wrong as I get towards the end here? Will super intelligent AI ignore humans, or will they destroy us? Big question out there. And there's this ideas sort of out there that we better be careful building artificial general intelligence or super intelligence because it's going to kill us all, maybe. It could destroy us all. Will it destroy humanity? Well, I think that's not what we have to worry about. We have to worry about the more mundane, where our training sets transfer bias. So Amazon scrapped an internal AI recruiting tool that was biased against women. But because what was its training data? What the human recruiters had seen and who they'd said to hire. And it turned out that there was a negative bias whenever a woman's CV mentioned being involved in a woman's group. There was a bias against them. That got transferred into the AI system. So that's one danger, that the training sets, just like the training set didn't teach redness for the self-driving car, it takes human biases. I think that's a thing we have to worry about. And then there's overhype by companies of what their system's going to be capable of. And we've seen IBM have some reversals of fortune. I think they overpromised with Watson. I'm willing to say that publicly. A lot of their customers thought it was overpromised. And they're suffering from that. And so that's another thing where people overpromise based on expectations of quick progress or transfer. But maybe we're completely off the track. We think we're going to build intelligent systems. Are we sure we can do it? The epitome of it is we humans have this super intelligent robot that's looks like us, is as intelligent as us. And we sort of have this belief we can do anything we put our minds to, ultimately. It may take a long time, but we can do it. What if you saw this scene? Two dolphins, dolphin A and dolphin B. Okay, nice dolphins. What if you then found out that dolphin B was a robot dolphin? Would you think that dolphin A had built dolphin B? Nah. No, the dolphin, they don't have opposable thumbs or even opposable flippers. No, they couldn't have done that. They're not smart enough. But we're smart enough to build, a humanoid robot that's just as intelligent. It may take a long time. Oh, maybe we're not. Maybe we're just not smart enough, and we think we are. Maybe we're not. And even if we are smart enough, are we going about it the right way? We have a certain approach to how we look at intelligence, which is really based on computation and our models of digital computers. And I'm not saying it doesn't have its place, but are we just not thinking with the right metaphors and thinking about the right things? There's a real danger that computation, along with Moore's law, has delivered this cocaine to us researchers for years and years and years. We think it's the best thing. Yeah, more computers, that's it. And maybe it's something else we should be thinking about. We don't know. But Alan Turing in 1950 said, we can only see a short distance ahead, but we can see plenty that needs to be done. And I think it's going to take a long time to get to general intelligence, but there's lots of stuff we can work on and make a real difference in the world by working on it. So thanks for your attention.
That, I think, was the crowning jewel of our lecture series.
Well, that's very kind.
We've had, and look, it goes to show, because the people standing who've been standing for over an hour are still standing, but I think it's because they're in rapt attention. That's paradox, which basically is a version of that says we're good at what we do because we've lived in that world and we've created a storage and processing tool that lives in that world, and then we create machines that help us with that, but their job is to help us and not learn the physical world. And you're arguing that to become us, they have to learn the physical world. And I think it just makes so much sense. So my question, I guess, is the idea where you ended on digital computing. Do we need a chemical computer to approximate a human? Because that's what we are. We use multisensory things. In the end, we have some sensory mechanism. We have some then chemical neuronal firing thing. Do we need a chemical computer? We call it a semi-analog computer. What is it, do you think, if there is a thing?
I don't know what it is, and it maybe isn't a different sort of thing.
Yeah.
It may be a different sort of intellectual tool. So calculus didn't change what the universe was made of, but it let people think about physical processes in new ways and solve all sorts of problems they couldn't solve without calculus. So we've got this tool which talks about a certain class of processes, i.e. computation, but it's only a certain class. Yeah. Maybe there's other ways we should be thinking about things, and they're better analogies. You know, I don't think it helps to understand how the planets move by thinking of them as computational devices. You're better off using classical mechanics. So I don't think it necessarily has to be a different physical instantiation, although maybe it does, but I suspect there's intellectual tools that we haven't quite got yet.
So there's a set of object tools that we would, if correctly described, we could build a thing that understood those things. That's probably true. Then the only other question I have, and then we'll open up to the audience, is obviously if I think about child learning and our vision system, I learn by running into things, right? Essentially, and I look for edges and in primitive vision, those edges become important because I learn that the boundary of a thing is a thing that's going to hurt me, and off I go. Does it have to be experiential in the end that we have to, because that seems to be how we learn. We don't learn physics, we learn running into things.
Yeah, although, you know, there's some things that argue the other way. You know, on the savannah, a gazelle pops out and it can run.
Knows the world.
It can run in 2 seconds because otherwise it's going to get it.
And its mother has never run, etc. In front of it.
Yeah, it just knows how to run. So I don't want to get too held up with exactly what humans can do. And there's lots of just so stories that do involve visual perception, but then people who are congenitally blind can also do all sorts of things.
See the physical world, yeah.
Yeah, in different ways. I would like to think that the physicalness is very helpful as a shortcut, gets us there. It certainly seems to be, as Johnson and the guy at Berkeley, whose name I forget right now, that we live on metaphors. We talk about everything through our spatial metaphors. So we're making progress towards a research goal. We're moving towards it. And
it always has a distance vector.
Yeah, and it's got a metaphor for our physicalness in the
implies
world.
That we're very comfortable with that.
We're very comfortable with that, and we use it all the time. And by the way, Turing computation is based on a very physical model. Yeah. There are containers, the squares that you have a symbol in or not in, and you move the tape. And our view of computers is that there's this row of containers in RAM memory. And Al, I was just reading your book with Hopcroft and Ullman the other day because I'm trying to narrow down where this. In 1974, when you wrote that book, the RAM and RASP models were sort of set in stone. You know, that's what computation is. We've got these containers, we put stuff in, we can change them, we can put them in and out. In fact, that's just a metaphor for what's happening because today's processors are not doing that at all.
No.
Memory is spread over 3 different cache hierarchies. There may be, I think the number for a x86 is that maybe as many as 160 instructions in flight in parallel, but we talk about them in
a sequential way that would make sense to us.
Yes.
Yeah. Great answer. So over to the audience. Well, Al, you have to go first because you've just been, what do you call it? You got the shout out there. Yeah. So Al Aho will go first.
Rodney, a brilliant talk. Thank you for coming and giving it. About a decade ago, Stephen Wolfram, the creator of Mathematica, asked me 2 questions. The first was, did I believe in the Church-Turing hypothesis? And I said, sure, Stephen, why not? And the next question was, do you believe that human beings are biological computers? And I said, sure, Stephen, why not? And then he said, well, since I answered yes to both his questions, what that means is that he could take my thought patterns and memories, program them into a computer, and at time t equals 0, the computer and I would be indistinguishable. How would you answer Wolfram's questions?
Well, I'm very worried that we may have missed something, and I'm not prepared to say yes to either of them. And the reason I was looking at your 1974 book over the weekend was I was trying to see when the Church-Turing thesis had become totally accepted. If you go back to a book written here in 1969 by Hopcroft and Ullman in their language recognition, they talk at some length over whether that is right or not. And Marvin Minsky's book in 1967 worries about it. By 1974, everyone had said, yeah, it's just, that's it. So I'm not sure about it. I'm not sure.
Go ahead. Microphone passes. Barbie, there you go.
Hi, I had a question about something that you didn't mention in your talk about ethics. And I'll take the example of an elder care provider. Nobody really has a problem if you take a current computer and you scale it up to 10 to the 9th, 10 to the 12th, 10 to the 15th, 10 to the 18th computational elements to come up with a much more capable machine to provide elder care. A lot of people would have a problem with taking a human embryo and genetically engineering it to have more empathy, maybe less intelligence, to customize that person into a customized elder care worker. So one path has a very big ethical problem. The other path, not so much. Can you comment on whether or not the path that doesn't use a human embryo, but uses a scaling up of technology, at some point we start running into ethical questions?
Yeah, you know, I used to say when I was much younger, and I thought the world was going to move much faster than it did, I used to say, my life will be complete when my graduate students feel bad about switching off one of their robots. So far, it's never happened. You know, I think in principle, that could be where we get to eventually. By the way, I thought your ethics question was going to go a totally different direction, so this is great that you went this way. I think we could get there eventually, but I don't think we're even close to that because we don't have any systems with intent. We don't have any systems that know that today is different from yesterday, except from looking at the clock on the, you know, in the internal thing. So I think we're just a long way from that. And I think it doesn't make a lot of sense to spend much time worrying about it because we don't know how the situation is going to be by the time we are in that situation. So philosophers can think about it, but I don't think it informs our current day thinking. Now, on the elder care robot with ethics, I think there are some ethics issues there. They're not the ethics issues that we see talked about, the trolley problem, for instance, in self-driving cars, where people say, well, you know, when you got the choice, do you kill the nun or do you kill the three thieves? You know, which way do you steer? And I say, well, you never have to face that problem as a human driver, so don't worry about that. But here's an elder care.
You mean the nuns and the thieves are in separate places?
Yeah, you got to go left or right, and you got to which I got to kill one group of them, the single nun or the three thieves, whose life is worth more. But here's an ethics problem for an elder care robot that might come about. The elder care robot was, is looking after someone elderly who, was starting to suffer from a little bit of dementia or something, and is getting them out of the bed in the morning, and the robot, through its sensors, notices that the person has pooped in their pants, and the person says, "Don't tell my daughter." Now, should the robot tell the daughter that we had a little accident this morning, or should it listen to the person? How much dementia is it allowed to have? And I don't think this is going to be a runtime ethics problem. I think this is going to be a policy that is probably baked in and agreed upon by all the parties at some point. But
yes,
there will be ethics.
Decency, not necessarily morality or something, right?
Yeah.
Yeah, which is a hard thing to encode. Bob Martin, you had a question there. And then to Bob's left goes next.
Thank you. Again, fabulous talk. Another topic around AI and robotics is whether the magic of the Industrial Revolution will be broken. Job creation equals job destruction. And, the example that I've heard on the other side that'll be okay is the empathy jobs. That one is so hard.
The which?
Empathy jobs.
The empathy jobs,
Yeah.
That'll be very hard. That aside, what's your view? Is this, there are always human needs that'll come up, or are you worried as well?
Yeah, so there's a few pieces I want to answer on that. I think there's been a hysteria about robots taking jobs. I don't think we're seeing that. There's up on the Mass Turnpike, there's a sign from the Prudential or something. You can't be replaced by a robot if you've already retired. There's this fear of robots taking away jobs. And I don't think it's the robots taking away the jobs. I think it's displacement of human labor, which we've certainly seen.
Yeah.
And we'll continue to see. And it's not necessarily just AI or robotics, it's digitalization. It's when the digital chains change how the structure of a job can happen because we've digitalized the ways information flow. So we didn't replace toll workers on the Mass Pike with robots. We replaced it with automatic deductions from credit cards associated over the web with your transponder number and the DMV having access to the DMV's license plates, which could be read by a neural network, and blah, blah, blah. A whole bunch of things. So it's much more complicated. I think we will continue to see displacement, which can be incredibly painful for the people that it happens to. I think that phrase you used, maybe it's the luck of the Industrial Revolution or the luck of mechanization of farms, that people got other jobs. The mechanization of farms was really bad for the horse population, by the way. Horse population went like that. So I don't know. And, we do fear the gig economy and whether, people do not have portable benefits, et cetera. Maybe we need to restructure our social networks, social safety net, which there's certain parts of politics don't want to consider, but may be forced to. So I think it's not going to be smooth sailing.
So I want to build on that because back to Moravec's paradox, the things humans are not good at are the things we've invented relatively recently. So he always used mathematical computation. We're really not built for that. We've trained ourselves with some simple rules, and some are better than others, but we're nowhere near as good as a computing system. Logistical tasks, we have to create complex workflows and things, and then we have to edit them, and we're not really very good at them relative to a machine executing a set of tasks and picking a task. Do you think it's those sort of procedural, processy, well-describable mathematical tasks that go first, and we should not worry too much about those because we're not really very good.
If that's your job,
you worry, yes.
Yeah, I think the transactional sorts of purely transactional job. The job of a toll taker was purely transactional.
Yeah, there was no real value add other than
10 seconds. It's like 10 seconds.
The physical part of it was meaningless.
Yeah.
Whereas the physical part of many tasks, mowing the lawn.
By the way, it was physically transferring a token.
Yeah, exactly.
A token for value.
So that one makes sense. Yeah, you're absolutely right. What I would say, my answer to this is always, that task was demeaning in some way. It doesn't mean it's not a job, but you could imagine that individual moved into another job that perhaps had more physical attributes to it, and physical I don't mean manual, I mean something that was more humanistic. That's a better job for that person. They may not, of course, feel that at the moment of the change. So I sort of think those are the things that go first, which is why we sort of focus on the industrial automation.
Yeah, but then there's what I call this is going to make us all so wealthy that we can sit around and write poetry and eat grapes.
It's Romanesque, yeah. That was my plan, actually, so I hope that's true. But, okay, further back. There we go.
Hi, thank you so much for your talk. That was really inspiring. I really loved your discussion of the elder care worker as an example for an application of AI. I think because it really returns the agency and dignity to the person being assisted?
Yeah, I would say I think the elderly want independence and dignity. And,
Absolutely.
And our current elder care systems often rob them of both those things.
You said independence and dignity.
Yes. Yeah. So
Carry on.
And to that point, I think agency as well. And I wanted to ask, so I think part of the process of aging involves not only an erosion of the physical capabilities, but also the internal model of existing. A lot of the examples you described showed robots assisting the physical sort of degradation, but do you think there's any application of an AI that could assist in the nurturing of the internal model of a human as the aging process sort of erodes that?
I think there could be, and I think someone should be working on it.
I think it's a very good idea.
Yeah.
That's for you back there, right?
Yeah, that's
Yeah.
Yeah. I don't have a good suggestion. I think it's a good idea, though. Yeah.
Oh, cool. I'm on it.
Okay.
She's an artist technologist.
Yes,
exactly.
Yes.
You get the highest hand up. There we go. You win right here.
Bob Gezelter, by the way, your ethics problem is also almost identical to the problem from 2001: A Space Odyssey, where HAL was ordered to investigate and keep secret at the same time, leading to, well, a disaster. Observation, we didn't talk at all about accountability. When we talk about a rule-based system, you can obviously do a back trace of what rules were triggered, and you can understand what happened. When you talk about the other categories, it's fuzzier. And one of the problems is, of course, not when things work well, but when they don't. Any thoughts?
Yeah, I mean, that's an issue, but I would point out that many of the arguments about that are based on the idea that people can explain why they did something, whereas probably often we're just making up stories.
Yeah.
I mean, we see that from a lot of psychological experiments, psychophysical experiments, split brain patients, that we are just willing to totally make up stories about why we think or why we did something. So, we actually have a problem, I believe, with the criminal justice system, which is based on a set of beliefs which are probably not correct about how humans operate. Now we're trying to say, okay, so what do we do with machines about that? Mm-hmm. Likewise, it's hard. We've never been able to, people say, well, we have to be able to understand why it did something, prove why it did something. We have gone for thousands of years with horses where we couldn't prove the behavior of a horse as correct or not. We did know you shouldn't stand behind a horse. We did know you shouldn't take a cigarette lighter and light it next to its eye. We sort of knew the general parameters in which we could operate horses, but sometimes they were just, individuals that did weird things, and we got through with it. So we may have to just live with statistical testing of some sort.
So when Jan was here, and actually David Eagleman, who you've also met, one or both of them claim that maybe our consciousness is our storytelling device. So it's actually not got any other purpose than it's a storytelling engine that makes us feel clever about who we are and to explain what we do when we can't explain it, but we've reached a level where we need to tell these stories because we've got to feel like we were purposeful. And so they would argue that it's an illusion that isn't anything other than a storytelling device that runs in the background and makes us feel special.
Yeah, I've written that it's actually a device God put there so he could do a very low communication rate check of whether we're good or not by looking at our consciousness instead of all the stuff below. It was just a summary for God to tell what we were really doing.
So it's a very good, your answer is, I mean, how the hell can we actually judge conscious machine when we're playing a game with ourselves to actually make ourselves feel special and worthy? Okay, the hands are going.
I think we should have a lower hand.
Lower hand. Now, Rodney's going to select his own questions.
And then two people to the left of that.
You brought up just now the business of stories. We're very good at building stories. We build narratives. I call them narratives of belief, which say, I know this, and if I do this, let's do this. So artificial intelligence, to me, will not be real until the machines can make up superstitions.
That could be. Yeah.
It's probably true.
Yeah. The woman 2 over and behind there, maybe. Yeah. Yeah. No, yeah.
Yes.
When do we know, that's real? It's a deep question, and I don't know the answer. Yeah. 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 Okay. So next question. Yeah.
So you said most of your talk was about how we should work on changing AI and like setting whatever we work on and whatever we achieve against the backdrop of how a child learns. And you set different designations for that, like 2-year-olds for their ability to see and perceive vision and all of that. So my question is that as like their abilities, the ability of a child changes because of digital learning and other devices that are coming up. As these change, what do you think like the effect will be on the restrictions that you've set or the designations that you've set?
Okay. Yeah.
Good question. Well done.
So
the high school group.
Yeah.
Well done. Round of applause for the high school question.
That's a good question. I'm going to come at it. I'm going to come at it through a chain. I wasn't saying, it was just the last part of the talk where I brought up the 2-year-old, 4-year-old, etc. Before that, I'd said these are things that people can do, the tasks like being an elder care worker. So unless we can't call our systems truly intelligent if they can't do these things people can do in terms of big tasks. On the 2-year-old, 4-year-old, etc., I think that if we do make progress there, it will help us towards getting intelligent robots. If it turns out that with devices, children are able to do so much more, well, unless we're using CRISPR to change their genes or put implants, it means that currently within their capabilities there is the seed of that in any case. So we should observe that and then okay, how do we get to that? And that will be another clue on how to get there. If you also want to allow CRISPR or other sorts of modifications, I'm going to leave that for the next generation.
Just halve all your numbers or double them all.
Yes.
Okay, 5 more questions because Rodney does have to leave at some point, and I've got a feeling we'll go on forever. But Rodney, you're picking now.
Oh no, I just saw some shorter hands.
Shorter hands and younger hands, but you have to speak, then, not just. Yeah, it's high school students who go for round 2. You've got a good question to kick things off.
He's back there. Put your hand up higher.
There we go. Well done.
Yeah.
All right, so earlier in the presentation you showed the neural network on a self-driving car messing up the distinction between a stop sign and a 45-mile-per-hour sign. So who should take the responsibility when a neural network like that mishaps and perhaps runs someone over? Who should take the responsibility for?
Yeah, I think that's actually maybe going to be a limiting factor on how quickly some of these technologies are adopted on answering those questions. We've had this model for a while that the insurance applies to the individual driver, but maybe it's going to have to change that the insurance applies to the car manufacturer or the software maker if it's Waymo, and there's going to be a lot of testing and pushing before we sort of agree on what makes sense there. It probably shouldn't be the individual owner of the car when it makes a stupid mistake like that. We have had lawsuits, when defective cars with deliberately defective parts being made.
Yeah.
But I think as we get more of these intelligent systems in our lives, the whole insurance industry and the whole blame industry, if you like, and I'm not saying blame industry in a bad way. We need the blame industry. We need to make sure that the actors act well and do the testing. I think that's really open and a real issue that may limit the rate of introduction of many of these.
It would sort of have to be.
We probably should have had more of it on Facebook, for instance.
Sure, that's a good point. You should have to be that way because if you buy a low-end car with a less good system, because that's your financial wherewithal, you can't be more blameworthy for that. But then the odd part is, should the low-end car manufacturer be more blameworthy because they're serving a need in a market and there's only so much R&D they can support? So it's a very difficult question, right? Because you'll take them out of business by them having more accidents.
Yeah,
and then
well,
the whole thing collapses.
for instance, now we think it's totally acceptable that housing standards say there should be flush toilets. At one point, a flush toilet was an expensive thing to have. We didn't think poor people should be made to get flush toilets. Yeah. Now we say every house has to have flush toilets. Yeah. You can't have non-flush toilets. Yeah. Because of the health
Exactly,
issues.
right? It becomes a mandate and then it has to get to a price point, but there's no guilt in a flush toilet.
Yeah.
Maybe.
In the old days, it was what you're flushing.
Okay, we'll stay over here. Red jacket next to Bob.
Hi, thank you so much for the talk. So there's a lot of areas that you've mentioned where there are people that are working on very hard, important problems. What do you think are the most contrarian questions or areas of either research or starting a company, innovation that exist, areas where people might not even be thinking to look that should be explored, or that you might be interested if you were just starting in the industry today?
I don't quite know I know the problem I want solved. I'm not quite sure how that fits exactly. I'm worried that there are too few players which are too powerful. Google, search, Facebook, etc. How can we get more competition, more players, more diversity in many of these systems, where it's not a winner-take-all? And maybe that requires some really good ideas that sort of break down the winner-take-all, and then that idea has to be a winner-take-all, but it's complicated. But that's what I would like to see, a little more competition and diversity rather than everyone glomming onto one thing. Now, if everyone is glomming onto one thing, that means that somehow the owners or the founders of that got something that really worked, but I'd like to see more competition happen somehow.
That's a very good answer generally about digital technology, I think. Go ahead, left of Bob, as will.
No, they need to hear it. They need to hear it.
So actually, to Ryan's question, is the bottleneck actually the data sets that these people are using to then teach the AI to do whatever it is it's programmed to do? And if it's the inputs and all the teaching, so I know that when you're logging onto a website, Google asks you, is that a car? And you have to, you're basically doing work for Google. And of course, they have some of the largest data sets in the world. So if we had public data sets where the general public universities could utilize those inputs just the same way everyone else could that help us decentralize the solutions a little bit?
Well, I think that's a slightly different point than I was making. I was making about the control of the companies. We have seen some good data sets. Fei-Fei Li at Stanford with ImageNet, she developed that. Then, of course, she went and headed up Google's efforts. So, I think I always get suspicious about any one data set because it's got implications behind it, and which is why in my talk I was talking about this elder care worker as a much more broader thing. If data sets tend to make everything narrow and perform on that data set, and I think the important stuff is a much broader thing, and it doesn't quite fit the data set model, and I don't quite know how to fix that. I'm not sure that makes sense, but to me it makes sense.
One of the things we had Stephen Friend here, and his idea of on the healthcare topic is a probabilistic map of likely outcomes for you, but which you constantly update based on everything you're doing and the measurements taken of you, and so you're given sort of guideposts of, this year you gained a bit of weight, and given your age and what you've been eating, the probabilities of negative outcomes given your genetic map are these, but it's not really concluding, it's sort of guiding. Do you think that in healthcare or perhaps in systems in general, what we need is guides that perhaps map and adapt and So we think of them in chemical terms, energy surfaces, where you know where to find minima, you know where to find maxima, and you just meander through that space, and that's really the role of an AI system, is perhaps to act as our intelligent guide in multidimensional spaces, one of which is healthcare. Does that make sense of a thing to aspire to from a human standpoint?
Yeah, except, my experience with some of these things, like tenure, was junior faculty saying, should I do X or Y, which is going to be better for my tenure case? And asking me that question on a daily basis.
Wow.
X and Y. So, I would hate to have, a dynamic score for my health. And
on an hourly basis.
On an hourly basis. And, I'm just driving around trying to get that. So I think we have to be careful with
But annual maybe.
Yeah. And as you know, some of these metrics for researchers can be the death of good research.
Of course.
Because people are just playing to the metric and not going out with the wild ideas. And I hope the guy in the red over there goes out with a wild idea and builds, companies that are competitive with all these other companies. But the metrics sort of, and the metrics and the data sets already imply the answer. And
they do,
the interesting stuff.
The energy surface you form implies you know answers. And
yeah, the interesting stuff is when you break out of that. And, it is Bell Labs. That's what you guys do.
That's what we do, yeah. Okay, we went for high hand over on the right. And then we'll do two more. So your hand's either going to be high or low, or you're going to have to do a Fortnite dance to be selected.
First of all, thank you. Do we need to lower the bar for certain applications? I'm thinking of your stop sign example. We're using a 100-year-old system of signage. Maybe the stop sign needs to emit something. And by the way, I'm a retired Army colonel, so I'll
work
on your...
Have you built a hospital?
I think actually what is going to happen with self-driving cars is they're not going to be a one-for-one substitution for our current cars. Exactly that. It's going to be a change of the infrastructure. Yeah. It's going to be a change of the road networks. When we introduce cars, just regular cars, we changed our cities. We rebuilt our cities. It didn't used to. Jaywalking was not a crime until the car manufacturers lobbied for it to be a crime. You were able to walk in the middle of the street and share it with the horses. So I think that's what's actually going to happen. But I'm also using that as a rhetorical point. If you say that these things are as intelligent as people, they better be able to do this recognize stop sign. But I think you're exactly right. We're going to change the structure of our cities and road networks, and it's going to take longer than people think.
So almost what you're talking about is a digital overlay on our physical overlay is one way to solve the problem. If we can't teach machines to understand the physical world, we create a complete digital overlay on that world that allows them to exist in it with a different set of sensors and knowledge systems.
Right, but we're going to pay an incredible price for that. So in my neighborhood in Cambridgeport, which is a network of one-way streets, there are temporary signs that get put up, roadwork here today. And if you also then have to put that in the digital overlay at the same time, it's going to make things a lot more
and then you have to reroute, and you have to know what to do about that information. You're right. Is it worth the effort? Is a question. Right? Okay, last question. We're going second row, and we'll do both of them then, because they both look eager.
So what are your thoughts on the balance between putting more faith in machines as AI develops and the growing worry about cybersecurity? Will that be a factor in the timeline for adoption of AI?
Yeah, there's cybersecurity is a terrible issue, and I think there's this other terrible issue that the crack cocaine, as I call it, of Moore's law, said we have to build software quickly, we have to get it out there, we have to keep producing it, and it's grown up to be a whole engineering discipline without the discipline. So we would never build bridges and put them in life affirming or threatening situations without
see if it worked.
Without testing. We don't even know how to do that testing for software, for both failures and for security. And so I think cybersecurity is one of the biggest threats to us right now. A lot of people saying, we have to worry about super intelligent AI. No, I think we have to worry about cybersecurity as a much more immediate concern for us all.
Last question of the day.
That's a lot of pressure.
It is.
But throughout your talk, you've talked a lot about comparing AI to humans or beyond humans. Do you have any thoughts on comparing them to, say, a pet or something that may be lower intelligence, such as the dolphin robot that you had showed in your talk as well?
Yeah. The end part where I said maybe we're not getting it right, I have a whole riff there on trying to do as well as a polyclad flatworm with 2,000 neurons. And we can't. So not even pets. There's just a lot of stuff we don't understand about how real animal systems at very low levels work. And they have some, the reason polyclad flatworms is you can, without going into too much detail, you can do brain transplants between them, and you can put you can put the brain in backwards or flipped over, and then it adapts and figures it out in this transplanted brain.
Is this something you've done yourself, Rodney?
No, it was actually done. It was actually done in the 50s, and I think a graduate student made a mistake and put one of the brains in the wrong way one day, and then a whole series of papers came from that. So there are amazing properties. It's like taking the CPU and putting it in the socket backwards, and it wriggles around and then works. After a while. 3 days in the case of this. So it's just totally different from what we understand how to do from an engineering point of view, and I think there's so much that we don't know that we think we know.
Somehow we end up optimistic at the end of this, I think, because I think the potential is huge. The limits, I think the excess of what's currently going on, I think, is bounded by saying mostly irrelevant stuff. Potential is huge, long way to the future, and we should feel somehow good.
Yeah, there was this, the end of the 19th century, people were thinking everything had been invented. I think we've hardly started. Yeah. So there's so much to do.
What a great way to end. That's it. You can't have a better ending than that. Thanks very much. We give you a weight.